Okay, here we go. All right, so welcome everyone. Thank you for tuning in this week. Just like last week, my name is Harry Byers. I'm the project manager for the NASA student launch team for the 2019-2020 school year. Today we're going to be going over Arduino and circuitry. I just want to talk briefly about what we're actually going to be covering today. So our goal is to achieve just a little bit of insight on how various electrical systems work. Specifically, we're going to be looking at basic circuits. The one that we're looking at is going to be a resistor LED circuit. So we're going to be trying to turn an LED on and off. That will give us a little bit of practice using Ohm's law. And then we're also going to take a look at introduction to using Arduino with the circuits that we use. So we're going to look at pinouts, programming, PWM, which we'll talk about in a little bit. And at the end, we're going to talk about battery selection and motor selection. And various component selections, I should add, but specifically those two. Just in case anyone's not familiar with these, we're gonna go over a little bit of basic nomenclature. Units and analogies. So you've seen a very common water flow analogy for a lot of these things. Potential difference. It's just a measure of electric potential relative to a reference that's measured in volts with a sign V. And you can think of that like water pressure. Current is how much energy is flowing through your circuit at any given point in time. That is measured in amperes, the sign A. It's kind of like your flow speed or volumetric flow. And then resistance is another parameter we're looking at today. That's measured with the ohms with the capital omega unit sign. And it's kind of like the thickness of your pipe. You can kind of see on the far right that it's constricting your flow, so it's going to cause less current. Resistance to flow. Specific components that we're going to look at is the LED or light emitting diode. Essentially, it's just a tiny light bulb. We look at the Arduino, which is a common brand of microcontroller, and more specifically, or I guess more generally, a microcontroller, which is a circuit used for automation. First things first, we're going to be looking at the Tinkercad Circuits simulation software to do a lot of this demonstration today. So first circuit that we're going to look at is in the bottom right. That's kind of like the circuits class schematic. Let's make a circuit with a battery, which is going to be these lines right here, a resistor, which is the zigzag line, and an LED, light emitting diode. So you can see we have a diode signal, and then two arrows pointing out means that it's emitting light. Again, this is a schematic. This is showing generally what our circuit's going to look like. So I'm going to change screens real quick. You can see here I'm on circuit. I'm on Tinkercad. I'm going to go ahead and click create a new circuit. See it load up. Okay. And I believe we're ready. So the three components we're looking at is a battery, resistor, and an LED. You see there's three different batteries we can use. We can use any of these batteries. For this, we're going to do a coin cell battery, which is 3 volts. We're also going to need a resistor. I'm going to go ahead and rotate this a little bit. Oh, there we go. And an LED. First things first, before we jump in, you can see that we have a positive end and a negative end on our battery. What this means, in case anyone's not aware of this, is that, like we talked about before, voltage difference. We have a voltage difference of 3 volts across the battery, meaning that relative to the negative end, the positive end has a total potential difference of 3 volts. This is our resistor. It looks a little weird, and this is our LED. You can see that there's an anode and a cathode on the LED. For the LED, when we're driving it forward, you're going to take your positive end and you're going to hook it to the anode. In real life, you can see how the diagram has a little bent wire. In real life, it would be the longer wire off the LED. For the cathode, we hook that to the negative end. So hooking this up, following our circuit schematic, we go from the positive end of the battery, or that longer line. Let's go to the resistor. I'm going to change this wire to red so we can see what it looks like, kind of that we know that's positive. move this over. We're going to take our resistor and we're going to hook it to our LED. Again, I'm going to make that one red just so we can see it a little better. And then we're going to take our LED and we're going to hook it to our negative end. Make that one black. Okay, so now we have our circuit made. Let's go ahead and start it. Hit the run simulation button, and this works, right? Kind of nice that the circuit schematic works, but you can see there, how do we know the properties of our components? How do we know the properties of our battery, our resistor, and our LED? If I take out the resistor, so I'm going to hover over it, hit delete, I'm just going to very quickly attach a wire to our LED. Let's run the simulation. We get a little notice here. Current through the LED is 61.9 milliamps, while the maximum recommended is 20 milliamps. So it gives us a little warning. What does that mean? That means that the maximum current through our LED can be 20 milliamps. So we're going to add, I keep doing that twice, we're going to add our resistor back real quick. And just like circuits class, we're going to go with Ohm's law. I've done a little bit of Googling beforehand, and I know that red LEDs have an on voltage of 2 volts. So you need, relative to this black wire, the green wire needs to be 2 volts. So this could be 10 volts and this could be 8. This could be 10,000 and this could be 9,998 volts. Doesn't matter as long as the difference is 2. And our current is 20 milliamps. I'm going to pull open the calculator real quick. You can see on the slide we have Ohm's law right there. V equals IR. V voltage, I current, and R resistance. We're going to solve for the resistance value for our resistor. So using a little bit of algebra, we can get R equals V over I. We have 3 volts. We need 2 here. So to get this line from 3 to 2, we need to drop 1 volt over this resistor. So it's going to be 1 divided by the current through our LED, which is 20 milliamps, right? And 20 milliamps is going to be, well, milliamp, meaning like 1,000 milliamps into 1 amp. Knowing our standard units is an amp, 20 milliamps is 20 thousandths of 1 amp. So we can go to 20 thousandths, which is 0.020. So 20 milliamps into 1 amp, hit equal, we get 50 ohms. So this is set at 1 kilo ohm. If I go to ohms, that's milliohms. Give me 1 second. 50 ohms. See that the bands change on the resistor. I'll play with that around again. I'm gonna change that to mega ohms. You can see the black band became a blue band. Those bands in real life will tell you what the resistance is of this resistor. Luckily for us, Tinkercad takes care of that for us. I'll post a chart on the box with this recording and with the PowerPoint and everything. So that way you can get a feel for what these bands mean, but for right now, we're not gonna worry about it. We have it set to 50 ohms, we're gonna run it. It works, right? Let's stop it and let's cut this in half. Let's cut this to 25 ohms. Oh, I said 35. Let's do 25. There we go. See the band's changed again. Let's run it. There we go. We're getting too much current through our resistor. If we actually go with too much current through it, take a 9-volt battery, very quickly hook it up, and run it, you actually blow it up. See, we're almost pulling 1 whole amp through that LED. That's bad. It will break it. Real quick, I'm gonna get rid of this. I'm gonna move this over real quick and you'll see why in a second. And I'm also gonna get rid of this. We're gonna add an on-off switch. You can see right here in the bottom right, we have the circuit diagram. So the only thing that's changing in our circuit is that we're shifting this resistor over and we're adding a switch. What this is gonna let us do is turn on and off our circuit. So I'm going to go with the side switch here. And again, looking at our terminals, we have terminal 1, common, and terminal 2. this is a slide switch. What this lets you do is if the switch is on this side, this is active. If the switch is on the other side, which you'll see when we simulate, this one's active. Doesn't really matter which one we use as long as we connect the right leads. So there, I'm going to connect my positive to the common, and then I want to turn on the resistor or the LED, so I'm going to hook my terminal to the resistor. Before I forget, let's set this back to 50 ohms so we don't blow up our resistor or LED. We're going to start our simulation. LED is off, switch is off. Turn it on, LED turns on. Pretty simple, right? And we're going to stop that. Okay. Things that we can do in real life that we can't do in the software is that we can, well, I say can't do in the software, we can do it in maybe in certain cases, and we can try that. We can dim the LED by changing the resistance value. It doesn't really show it that well here. You can see that if we have too little resistance, it says, oh, you're running too much current. But we can try changing this and see what happens, right? So what if we change this to 5 kilo ohms? It does dim, right? So I'm set at the 50. Let me stop. Where's potentiometer? So potentiometer, I have it listed there, is like a variable resistor. So before I do this, let's look at our leads, terminal 1, the wiper, and terminal 2. So I can do terminal 1, or sorry, the wiper, and terminal 2, just to choose one. And we'll set this resistance to 5 kilo ohms. So that means when this is turned all the way on, we're at 5 kilo ohms, turned all the way off, we're at 0. So we can start the simulation and it turns on. If I turn it on, does it work? It gets brighter. So actually this side is off, this is on. We can dim it. That's a way to control our circuit. We can add another type of resistor called a photodiode. Let's see if we have it here. Or photoresistor, I'm sorry. And what this does is it acts like a normal resistor, but like the name suggests, photo, it changes based on the light level. Let's see, we can. Thought there was a way to switch it, but there might not be. That's okay. So the way this would work in real life, you turn your circuit on, it's just on. You shine a light on this, and I want to say, oh, here we go. More light, less light. So you can see that when it's dark outside, the LED dims. When it's light outside, it brightens. Can you all see that okay? Just type in chat or something real quick, like a yes or no, if you can actually see it dimming, since I've been talking about it. Thank you, Trevor. Moving on, or I guess before we move on, I just wanted to go over those ways that we could control the circuit without having any sort of like built-in logic, just using different circuit elements. Let's see. So now next we're going to move on to an Arduino. And real quick, I want to go over what is an Arduino in case anyone doesn't know. Briefly stated before, it's a microcontroller. It comes in all shapes and sizes. So we're going to use some Arduino Uno, which is just a model that's here in the software. There's an Arduino Nano, which uses the same processor as an Arduino Uno. It's just a lot smaller. There's the Mini, Micro, and there's a plethora more that I just don't have listed here. Differences between them is how many pins they have for input and output, how much power do they use, their physical size, the microcontroller that's attached to them, which kind of determines all those things, and what they're good for. Talked about before, it's used for automation, be more specific, controlling motors, reading sensors, doing light calculations, light as in not hard calculations. You know, you can't really do iterative solving methods on an Arduino, but it's good for just adding numbers together, doing multiplication real fast. Really, it's not a computer. It's meant for light tasks. If you want to do something heavier, you'd have to use a computer to interface with the Arduino. It's programmable. You decide what its function is. You tell it what to do, and it's programmed technically in C++, but luckily Arduino makes it really easy. They provide a lot of libraries to help you, as a beginner programmer, use it. It's very popular. Many DIY projects use Arduino. So we're going to recreate this circuit, maybe without the photodiode, or we can use the photodiode with an Arduino. We're gonna start with like a very basic usage. So I'm gonna get rid of these things. I'm actually gonna go to starters, Arduino. Let's go with fade. For now, you see I already built our circuit for us. Oh, sorry. I'll go over this again. Let me hit OK. Let me delete all this stuff. So again, we started in components basic, up in this top right. Go down to Arduino. I'm gonna go with fade. There we go. Move this over actually. Okay. And we have our circuit set up already nicely for us. So very basic usage, Arduino Connect as a battery. So I'm actually gonna go to code now, or actually, yeah, go to code. There's a lot of stuff here. Let's see. Give me 1 second. Let's actually pull out the blink circuit on top of this one. I apologize for that. Drag those over so it's a little bit separated. We're going to go back to code. Arduino over here. We're going to use it as a battery. So I'm actually going to get rid of this. I'm just going to make this something ridiculous, like 500 seconds, whatever. But you can see little code snippets over here. I should explain, this is what Tinkercad uses to program Arduino. It's this drag and drop block-based system. If you're very unfamiliar with how to program anything, this is very useful. If you're a little more experienced, something you can do is go to this drop-down menu. You can see the actual, it says, are you sure? Okay, continue. If you were programming Arduino on your computer, this is what it looks like. You have to enter everything manually. You know, if I want to get rid of this, I can just do this. There we go. Now I don't even have to worry about that. I don't even have to worry about this delay. It just won't happen. It'll just turn on the LED if I run this. So I'm going to start it, and it just turns it on, right? And that's how we use the Arduino as a battery. So imagine our circuit schematic. Instead of this battery, we just have the Arduino. Remember that we had our ground connected to the negative end of our battery, and this green wire would have been connected to the positive end of our battery. Now instead we have it connected to the ground pin of the Arduino and pin 13 of the Arduino. Now you've seen it with a switch, slightly more advanced, we can make it turn it on and off. So I'm going to uncomment these, or if I go to my blocks, continue, you can see it there. Set built-in LED to high, wait 1 second, wait 1 second. The built-in LED on the Arduino automatically connects to pin 13, which is why this works. Something else we can do is we can drag this off. If I can move that, delete this. Let's see, delete block. Move some of this stuff. Takes a little bit to get used to. Recreate this. Pin, scroll down, 13. Low. So I recreated the code that was being used, but I just changed it to be more verbose in what we're doing. So we're going to turn the pin on. The LED will turn on for 1 second, then it will turn off for 1 second and repeat until we get tired of it and turn it off ourselves. So let's go ahead and start the simulation. 1 second's on, 1 second off, 1 second on, 1 second off. Right? Got a message from Duke. Yes, it is being recorded. That's how we can use it as a switch. So like we had the slide switch in there, we can use it with the Arduino. And we could do stuff even more complicated where if we have buttons connected to other pins, we can read those inputs. You can see there's output, input, so I can read a digital pin or an analog pin. There's different control methods for all sorts of programming. So there's a counter, which is like a for loop, if statements, repeat statements, which are while loops, and the delay. So there's the wait. We can do math here. Different functions. I'm sorry, I click a lot. But you can see that there's different functions available. We can create variables. So we can create a variable A. Why not? And it will automatically handle using these variables, doing everything that you need your microcontroller to do with these blocks. What I would recommend is that if you're not comfortable with programming, use this to create your circuit, create your circuit, create your code. Then come over here, blocks and text. You could see as you add stuff, it adds it, right? So if I change that 0 to a 50, it'll change that to 50. If I change this to 50.5, see what happens, or 0.5. Maybe I can't change that. This should be a floaty point value. I was hoping that would change, but it didn't, which is okay. But I'm going to run with the assumption that this will handle doing a lot of that programming for you. Oh, and what I was getting to is that once you create your script, you can actually just copy paste this over to your Arduino software and build it onto your physical Arduino. So now we're going to talk more about PWM. It's a phrase that I threw out earlier. It's pulse width modulation. Let's go ahead and blow this up. What does this allow us to do? It allows us to send an on and off signal to our circuit very fast. So if we were to take that slide switch and flicker it really fast, the LED would actually seem to be, to us, to be dimmer than it actually is. So it's another way of dimming an LED. So there's really two methods you can do it: through resistive dimming by changing the resistance value, or by turning it on and off very fast, like flickering the lights in your house. There's a visual representation of what this actually is. So you can see 0%, which would be completely off. There is no on or off, with the upper level being on, lower level being off. 25% would correspond to a 25% dim, or 25% of the full brightness of that LED. So for a quarter of the time, the circuit is on, and for 3/4 of the time, the circuit is off. And then And then 100% would be the circuit is just on. And then you can see here what PWM hopes to achieve. I know it's a little blurry, I apologize. But you can see as we go from 0, 25, 50, 75, and 100, it's approximating that analog signal. Moving, okay, I apologize. Take a step back. Let's go ahead and delete this. Yes, go ahead and delete that. We're going to go to the glow Arduino circuit that we pulled up earlier. You see that the code's a little more complex. Now we're using some of that control software. So it's saying count up by 5 from 0 to 255. Then we're going to set pin 9 to that value. We're going to wait, and then we're going to keep going all the way up to 255, then reverse, go all the way down to 0. Oh, I'm still on the PowerPoint. I'm sorry. So again, we got rid of the other circuit. In case you don't have this one pulled up, starters, Arduino, we're on fade. Go back to the code. Like I was saying before, even though none of you could see it, we're going to count up by 5 from 0 to 255, and we're going to give that value to brightness. We're going to set our 9th pin to brightness, wait 30 milliseconds, and then we're going to go all the way down once we hit 255. If we run this, you can see what that does. Zoom in. Cycling through that dimming pattern for our LED. Stop simulation, let's look at the code. And you can see here that it automatically wrote the code for us. So if we wanted to do this in real life, what we could do is just copy paste this code, put it into our Arduino software, build it to a real Arduino, and then run it, and it would work, as long as we had the same circuit set up. While we're here, I want to talk a little bit about using the Arduino as a battery, and how before in the example we went through Ohm's law to determine the resistance value. Notice that we had 50 ohms for 3 volts. Now we have 220 ohms for the Arduino. Real quick, what this corresponds to is this corresponds to a 5-volt output voltage from these pins. So for an Arduino, each of these pins can output a maximum of 5 volts at 40 milliamps. And that's very important to keep in mind when you're trying to control things like motors, control things like LEDs, is that you need to make sure that it's not going to draw more than 40 milliamps, because it will blow up your Arduino. It won't catch on fire or anything, but it will ruin it. Luckily, like I said before, the red LED handles 20 milliamps at 2 volts. So using Ohm's law, like we did before, we can actually do that. So we need 2 volts over this, and we can supply 5. So it's a total difference over the over the resistor of 3 at 20 milliamps. So if I do 3 divided by 0.02, 150 is actually the minimum of what we need. They use 220. So what if we change that? 3 divided by 40, 75. So they went with a more conservative value for resistance. The minimum would be 150. So if I change this to 150, it should still work. And you can see it's functioning fine. If I go with 75, start simulation, it's actually working okay. And that's probably, oh, no, you can see when it actually goes all the way on, we overcome that current capacity for the LED. And then if we go all the way to 0, actually, I don't know. I don't think this would blow up, just because I don't know if that can draw more, but we can try going all the way to 0 resistance, see what happens. Anything? It just draws more current. The Arduino doesn't seem to be giving any gripes with it, but you can see that we're drawing over 40 at some points during our cycle. That would be bad for the Arduino. Moving on, beyond LEDs, where can we apply this sample circuit of just the battery, resistor, and LED? This type of circuit was sort of plug and play. You know, you plug in your resistor, you plug in your LED to the battery or to your Arduino, turn it on, and it works. A lot of things are like this relating to rocketry. Flight computers are like this. You know, the Stratologger, the Telemetrum, Easy Mini, Merlin Missile Works, flight computers, you have to give them a battery, you have to give them a switch to turn it on. Beyond that, you just let them go. As long as you fulfill the requirements that they have, which we'll talk about in a little bit, they should work. You can also use them to control DC motors, servo motors, stepper motors, other things like that, other motors, which is important for payloads or recovery designs if you're not using pyrotechnics. You can also use it to troubleshoot existing systems. So I say think back to this year's payload, what was happening with the circuitry. The car burned out, right? So we had to look at the circuitry and see, oh, for some reason one of the contacts was missing for the power switch. So power was never making it to the circuit. Understanding how these circuits work, even at a very basic level, could just help you look at it and be like, okay, following the line, this doesn't make sense. Like, it's not performing the way it should because one reason or the other. we can use this Arduino. I'm going to go back to it this time so you can actually see what I'm doing. What if we get rid of the ground wire? Then what happens? So I'm actually going to delete this. Let's start it. Nothing's happening, right? The circuit's not complete. I'm going to actually backtrack on the slides and go to this circuit right here. These black lines are wires. If there's a cut in them, if I go back one more or two more, the switch is simulating a cut in the wire. If it's open, it's going to be off. If it's solid, the circuit will be on and functioning however you designed it to work. If I connect this again and run it, you can see that it works again for our bad resistance values, and it's screaming at us, but that's okay. We can also use this to make informed decisions on what our components should be for our circuit, understanding what we want to achieve with our circuit. So in this case, it'd be, I apologize. In this case, it would be dimming the LED. It could be moving a servo, which actually we can look at. Let's see. Yeah, let's look at it real quick. So I'm actually going to get rid of these circuits. Again, this time on the circuit page so everyone can follow along. Or you can see down here at the bottom right, there's servo. So let's take that in. Move this down a little bit. I can't move that far. Ooh, escape. You see that Tinkercad already took care of hooking it up for us. Servo wire, I'm going to recolor this, comes in a certain flavor of what is called servo wire. It's what plugs into the Arduino to control the servo. So the brown line would be, as you can see, follow it down to the ground. It would be the negative end if this was like a battery. The red line is 5 volts power to the servo, and the orange wire is the signal line. So like how we used that green line before to dim the LED, this is the signal that you'd send to your servo. The reason why you have 3 is because you have to always have 5 volts to your servo motor. The signal line just tells it when to move, but it is a 5-volt signal. So there's a little bit of difference there, but for all intents and purposes, it's pretty simple to just follow the circuit schematic, plug in a servo, and let it go, and it will work. However, one thing before we move on, I would not recommend connecting the servo directly to your Arduino. It might be okay, but like I said, 40 milliamps is the max. I believe off the 5-volt pin, it's 500 milliamps, or maybe 1 amp for the Uno. So it might be okay, but if you're powering anything bigger, you're going to want to have a separate power circuit. But for now, we're just going to run with this. Let's see what it's doing. So imagine your servo is like an LED, off, dimming, dimming, or I guess brightening, all the way on, dimming, all the way off. Look at the code. It's set up pretty similar. We're just changing, instead of a brightness value from 0 to 255, we're changing an angle from 1 to 180. And we're going to be just going through that. Get it all the way up to 180, then bring it all the way down to 0 and repeat. Let's look at the, stop the simulation, let's look at the code itself, and you can see how you would do that here. And again, if you wanted to do that for whatever reason, you could copy paste this, put it in. Something that's important to note with Arduino, the inclusion statements. These include libraries. So for the servo, you need a special servo library to use them. Otherwise, you'd have to program it like you would with the LED, like the set pin to something, a value. The servo library takes care of all the math to get 0 to 255 to 0 to 180. And I think at this point, it's good to mention why 255. You know, for the servo, 0 to 180 is pretty self-explanatory, 0 degrees, 180 degrees. For the LED, it's 0 to 255. The reason why is because when you're using pulse width modulation, the signal command is a byte, 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 computer byte, which is a integer value from 0 to 255. So it's kind of, if I actually type it out over here, you can see, let's see if I can do this somewhere. Maybe I have to go all the way to text. Continue. So see here at the bottom, I'm going to type it out real quick just for us to see. 1, 2, 3, 4, 5, 6, 7, 8. This is 1 byte. 255 would look like this. 1, 2, 3, 4, 5, 6, 7, 8. 254. 253. It's filling up the byte with ones, and it's a binary number. Let's move on. We're going to talk about battery types. We're going to talk about component selection, and then we're going to talk about motor types as well. We used the coin cell battery in our first circuit just because it was there. You saw there's also 9-volt batteries. There was also an option for AA batteries. Those are the common batteries that you'd find in like household electronics. You probably bought them at the store before. For our not so common battery types, maybe common to us, but not common in a household, there's 3 that we should note. There are a lot of others. Based on your needs, you're going to want to look those up. But in general, there's a lithium ion battery, lithium polymer battery, or a LiPo, and the nickel metal hydride battery, or an IMH. Starting from top to bottom with the images directly on the right, lithium ion looks like a AA battery. It tends to be in a blue wrapper, at least from what we've had at CDME. They have high energy capacities, so one cell, for example, that cell on the right would be measured energy capacity would be 2200 milliamp hours. What that means, a milliamp hour means that 1 milliamp hour means that the battery can supply 1 milliamp of current for 1 hour. So 2200 milliamp hours is 2200 milliamps for 1 hour, or 2.2 amps for 1 hour. Going to the LED, if we take 20 milliamps, we have a 2200 milliamp hour battery. We could supply that for a long time, right? 0.02 amps, we can actually calculate that. I closed out of the calculator, but that'd be what? 2200 divided by 0.02. So pretty big number, right? Probably over 100 hours. I believe it'd be 110, right? Has a low discharge rate. You cannot power a motor from this, probably, maybe small ones. Discharge rate might be the same as, might only be able to supply 2 amps, whereas maybe you need 40 amps to run your brushless motor. Whereas on the flip side, a lithium polymer battery has high energy capacity and high discharge rates. So you can get lithium polymer batteries that supply 40, 50, 70 amps of current, but they're dangerous. You have a lot more safety precautions with them. If you puncture them, they're going to explode. They're a little more finicky to work with. They're a lot more fragile than lithium ion. An older type of battery that's like very common, like RC electronics or rechargeable home electronics that you're not supposed to open, is nickel metal hydride. They're relatively safe. They have high discharge rates, but they're less efficient than lithium-based batteries. Less efficient meaning that they're heavier. So for the same size battery, maybe if you had the cell the same size as that lithium ion cell, you can get 2200 milliamp hours out of that battery. You might only get 1000 milliamp hours out of the nickel metal hydride battery. Moving on, motor types real quick. Servo motors, brushless DC motors, and stepper motors are really the big 3 that I consider. A servo motor is controlled with pulse width modulation. So just like we showed in that example, dimming the LED, or like we did, moving the servo arm, based on what you input, you can move it to a desired angle. Very commonly used in robotics. This year on the payload, we used it to move the arm on the car. We also use them to move the set screws for the retention system, but you can see that there may have been better options depending on what you wanted. Space-wise, maybe the servo is pretty small. Stepper motors can be bigger. And again, it depends on what you want. Brushless DC motor, that's a continuous rotation motor that's useful for drivetrains. So on our rover, there's one built in to move the wheels. They can be controlled like a servo with special circuitry. And what I mean by controlled is that like you dim an LED, you control the rate of rotation of that DC motor with special circuitry called an ESC, or electronic speed controller. We had that on our payload this year. You know, you have your controller and you have like a throttle. You put the throttle all the way up, it goes 100% speed, and the car is flying across the room. Tone down the throttle, the car slows down, right? Pretty simple to understand. It's continuous rotation. You just use it if you want something to rotate, pretty much like a wheel. Stepper motors is kind of a mix between a brushless DC motor and a servo motor. I say that because it's a DC motor that moves in steps. It's not continuous. You can have it rotate continuously, and it allows for very fine controls. That's the type of motor that's used on a 3D printer because you need to know those XY coordinates in order to print your parts out accurately, right? You can mix and match these a little bit. Like I say, brushless DC motors, continuous rotation. A servo motor has a brushless DC motor in it. A stepper motor has a brushless DC motor in it, but it's just a special type of brushless DC motor. Whereas a servo uses a brushless DC motor and a little more circuitry to get it to only go to those angles. But you can modify those servo motors to be continuous rotation. And you can get it to act like, you can modify those servo motors to act like a stepper motor. You can use a stepper motor to act like a servo motor. You can even put a shaft encoder on a brushless DC motor to measure how far it's rotating if it's not a stepper motor. So it's still going to rotate continuously, but it will spin a certain device that will tell you how much have you rotated, and you can use it like a stepper or servo motor. The thing that you're going to look out for, moving on, is how to pick these components. How do we choose the battery? How do we choose those motors? How do we choose sensors? Anything that we're plugging into our circuits, anything we're putting into our systems, how do we choose them? You're going to pick them based on your functionality requirements and electrical parameter constraints. What I mean by that is for components like your sensors and your motors, like we were just talking about, weight. So maybe you want to modify a servo motor to act like a stepper motor because it weighs so much less. So it might be your best option there. What is your input voltage? You know, your Arduino can take, I believe it's 7.5 to 12 volts to turn on. It supplies 5. So if you have a 12-volt battery, yeah, you can turn on your Arduino with that, but you might blow up your LED if you're running your LED off of only the battery. You know, so what is that voltage that you need? What is your draw current? So the Arduino might take 1 amp to run, even if nothing's plugged into it. And then now you start plugging things into it, and now it's drawing more and more current. You're gonna have to keep track of that to figure out what your battery is. It's important to just know all those parameters for your components so that you can keep track of them, make sure they're all compatible, make sure things are going to work the way you want them to work. For batteries, again, weight, output voltage, discharge rate, and energy capacity. So weight, you're going to know how heavy your battery is. So nickel metal hydride battery might be reliable, but it's heavy. We have used lithium polymer batteries. We have used lithium ion batteries because they are lighter and they fulfill our needs on the rocket. Output voltage, you know, you're gonna have to look into, again, like I was just talking about, what is the voltage of your components? Like what voltage difference do they need to even turn on? What is the discharge rate? So like I was talking about, keeping track of all those draw currents, sum those up and figure out what the total current draw on your battery is going to need to be, and make sure your battery can supply that, and for how long. You know how long your system's on, so you can determine how long does your battery need to last, and that's kind of playing back into that milliamp hour rating. And energy capacity, again, that kind of plays in the weight, that kind of plays into the system of, you know, if the battery fails, then what happens. Keeping those in mind as you make that decision. Keep things simple. Don't overcomplicate your circuits. like I said, a lot of things are plug and play. However, there might be options to make something yourself. There might be options to buy other boards that can do what you want to do. There's trade-offs to those, but just keep it simple. Don't overcomplicate your designs. Identify the function of your circuit. Identify the function of each part of your circuit so you know what it's doing, and your design should go pretty smoothly. Keep it consistent. What I mean by that is make sure everything's compatible. This year we had issues where we had a certain battery, but it was plugged directly into a board. That board did not take the correct voltage from, like, it required a different voltage than the battery could supply, and it required a lot less current than the battery gave. But you saw that while our LED required 20 milliamps, if you plug just a battery into it, it's not going to draw only 20 milliamps. It's going to draw as much as it can take, which is the reason why we have the resistor. A lot of things that you buy that are plug and play will automatically handle drawing that current and saying, you know, if you bought a breakout board for your LED, it would already have resistors built in to limit that current to 20 milliamps. But if you just have the component alone, it's going to draw as much as it physically can until it breaks. So backtracking to what I was talking about before, we had a board that took different input voltage, didn't turn on. We have boards that took different current requirements than what the battery was giving it, and they actually caught on fire. So those are things that you need to worry about while you're designing these circuits. It's kind of like a feedback loop of you choose your components, look at the requirements, choose your batteries, and then that kind of goes back and you just make sure that everything's fitting, and then you just iterate through until you get something that looks good and will work. Moving on, that's really all I have to show you this week. I know it's pretty light on the demonstration side, again, because Tinkercad makes it really nice to handle a lot of the hard stuff for us, like the programming, setting up some of those Arduino circuits. So if you want to play around with circuits, figure out how they work, this is a quite literally free way to do that. You don't have to waste money buying components and blowing them up yourself. You can just blow them up in here. And I can vouch for that it's pretty accurate. You saw that we did Ohm's law here and it worked on that LED circuit. It has a way of simulating all those parameters for us. And I'm going to open the floor to questions now. Feel free to unmute yourself and ask a question if you have any. If not, that'll be it for the night. Any questions? So David says, what have we used LiPo batteries for in the past? We've used LiPo batteries for usually driving motors. So I've worked on various projects for the rocket. The flywheel project namely used a LiPo battery to power the motor. For avionics, we've used LiPo batteries for setting off E-matches. And we've used them for backup power systems. So E-matches is kind of like a specialized resistor where you push so much power through it or so much current through it at a certain voltage that it does, like a match does, light on fire and set off our ejection charges. Powering the flight computer, the lithium-ion battery may not be able to supply the current required to set off the E-match, so we also have the LiPo battery. That being said, flight computers also have circuitry on there to build up a store of energy to send a pulse out to those E-matches. So it really depends on the circuit design that you have going on. But that's really what we've been using the LiPo batteries for, just things that require more current draw. Mike asks, what parts of our BSLI rockets are Arduinos used for? He says, I assume to measure altitude and for payloads. Others. Yeah, you're right. Measuring altitude and payload. So a lot of the little CubeSat payloads that we build use Arduinos for running the sensors, running the sensors. So briefly going in there, altimeters, accelerometers, whatever the experiment on board is. Arduino can read those. So actually, let's go back real quick. Going back to the circuit. This is something I probably should have said earlier, but let's go over the pins on the Arduino. You can see that on the Uno, it's pretty labeled of what everything is: a digital pin, analog pin, and power pin. Digital pin is an input-output pin, so it can receive 5 volts on or off. You can read that, so you can either supply 5 volts, or you can say, am I receiving 5 volts through this pin? Analog pin does something similar, where it can supply 5 volts on, or it can read anything between 0 and whatever your reference is, up to 5 volts. So with the AREF pin, you can supply 2 volts to it, and then this analog pin is going to be reading 0 to 2 volts. By default, it'll be reading 0 to 5, but you can hook up a temperature sensor here that reads 0 to 5 volts and fit that to a curve that says 0 volts is 0 degrees Celsius and 5 volts is 100 degrees Celsius, and you can read a sensor that way. There are more advanced ways to do that as well. You could see that there's the transmission and receiving pins. There are pins for different types of input and output in the digital pins that you can use different ways to receive data. A lot of different sensors use the digital pins for input output as opposed to the analog pins, but some of the cheaper sensors do use analog pins. But to go back, yeah, I used it for reading sensors. I've personally used it in the past on the rocket for controlling motors for a specialized payload. Not necessarily anything flight critical, but that's what you would use it for. Any other questions? Anything that we went over that anyone wants more information on? Going to assume that no one has any more questions unless one comes through like right now. If not, thank you all for tuning in. I know it's kind of like a little shorter one, a little different than last week's. But I'm glad there's interest in this. So thank you for tuning in, and I will see you all next week.